All right, why don't we go ahead and get started? Welcome, everybody. My name is Jen Tang, and I am the Director of Community Relations at Lawrence Berkeley National Laboratory. And thank you so much for joining us this afternoon for the last lecture in our 90th anniversary speaker series. Let me actually stop sharing screen. So as many of you know, if you've been joining us for these lectures, our lab was founded in 1931. And since then, the lab's been dedicated to advancing the scope of human knowledge and seeking science solutions to some of the greatest problems facing humankind. In celebration of the lab's 90th birthday this year, we've developed an array of content, including podcasts, virtual tours, historical highlights, a charitable giving campaign, and this speaker series, all intended to shine a spotlight on the lab's unique approach to team-based and pioneering discovery science. As we reflect on our past achievements and imagine what the next 90 years might bring, we invite you to explore our 90th anniversary website, which has links to all of that great content. We'll put that in the chat for you soon. Before we get started, let me cover a few housekeeping items. First, we are recording this webinar, so people who aren't able to watch it live can access it later on our YouTube site. There will be a Q&A session following the speakers' presentations, and you can submit questions at any time during the presentations using either the chat function or the Q&A function at the bottom of the Zoom window. Now, before I introduce our first speaker, I just want to thank my colleagues in government and community relations, strategic communications, and IT, because without their help, this event would not have come together. So with that, it is my pleasure to introduce our first speaker, Natalie Rowe. Natalie is our Associate Laboratory Director for Physical Sciences at the lab. And Natalie, the floor is yours.
Thank you so much, Jen. Let me share my screen and get started here to introduce what I hope will be a really exciting series of talks. So our theme is Unlocking the Mysteries of the Universe. And we have a long history here at Berkeley Lab in particle physics and cosmology. In fact, it goes back to our founding in 1931 by Ernest Orlando Lawrence. He invented the cyclotron, and for that he received the Nobel Prize in 1939. That was the first of the lab's 14 Nobel Prizes. 6 of them having been awarded in physics, and they're listed here. So you can see the many discoveries that we've made of new particles, inventing new types of instrumentation, and making groundbreaking observations about our universe. And you can read more about all of the Nobel Prizes awarded to the lab at the link there at the bottom. So this long history in particle physics and cosmology allows us to attempt something really audacious, which is to connect the quantum with the cosmic, to understand the evolution of the universe from the dawn of time, the Big Bang, when it was a hot, dense soup of particles. And through our studies of particle physics, we believe we understand the fundamental particles and their forces here. And if we understand those particles and forces in a hot, dense plasma at the beginning of the universe, we can hope to try to understand the evolution of those particles. But as we try to trace this out, and you're going to hear more about this in each of the following 3 talks, we continually run into surprises. For example, early in after the Big Bang, we believe there was a period of exponential expansion due to something we call inflation. And as the universe expanded and cooled, eventually began to form atoms and molecules. And at that moment, the plasma cooled and photons were released, and this created the cosmic microwave background radiation shown here. And this gives us a fingerprint of the early universe, the infant universe at the age of 380,000 years. Now, as the universe continued to expand and cool, it began to decelerate because gravity is such an attractive force on long ranges, on long scales. And we expected that it would continue to decelerate and perhaps end up in a final crunch. And experiments led by scientists at Berkeley Lab discovered, trying to measure this deceleration parameter, that in fact, it is now accelerating again. And we call this acceleration dark energy because we don't know what the force is that is overcoming gravity and causing the universe to expand again. And perhaps this acceleration is related to the earlier inflationary expansion, but we honestly don't know. So there are many mysteries. And in fact, our universe today consists of, in its energy budget, over 70% dark energy. Then there's another 24% or so due to dark matter, a form of matter that is not part of the particles that have been discovered by particle physicists over the last century. It is dark because it does not emit electromagnetic radiation, and we're on the hunt to try to figure out what it could be. And in fact, only less than 5% of the universe is due to ordinary matter, the atoms that make up us and our Earth and the stars and planets. So there are many, many mysteries to be solved in the universe today. And in addition, we believe that after the Big Bang, there was equal amounts of antimatter, and that has disappeared. So we don't know what happened to the antimatter. So in the quest to connect the quantum and the cosmic, we have these big questions that we're trying to address. What happened just after the Big Bang with this inflationary period? What happened to all the antimatter? What is dark energy? What is dark matter? And what is the nature of neutrinos, the neutral and almost massless particles that stream throughout the cosmos? So you're going to learn about how we're addressing these questions because the nuclear and particle physics communities have put in place experimental plans to actually design experiments and answer these questions. We've written reports outlining the projects that we want to carry out to address these questions. And Berkeley Lab is playing leading roles in 3 of these experiments that you'll be learning more about: the CMB-S4, the Cosmic Microwave Background Stage 4 experiment, the CUPID experiment looking at neutrinos, and the DESI experiment studying dark energy. So I hope you'll enjoy the presentations coming up. And with that, I'd like to introduce Julian Borrill. Julian is a senior scientist in the physics division. He's a co-spokesperson of the CMB-S4 experiment, and he'll tell you more about that early fingerprint on the universe from the cosmic microwave background radiation.
Thank you very much. So for as long as people have looked up at the sky, they've asked questions about the origins and the fate of the universe. And in our current scientific understanding of the history of the universe, we start with a hot Big Bang, followed by this period of exponentially fast expansion called inflation. The expanding and cooling universe, in that universe, the protons gobble up, as the universe expands and cools, the protons eventually gobble up the free electrons to form hydrogen atoms, and the light of the big set free. The hydrogen then slowly collapses into clouds of gas that eventually get massive enough to ignite nuclear fusion, lighting the first stars. And this starlight is energetic enough to separate the electrons and protons again, and the universe reionizes. The dark matter in the universe coalesces to form a web of invisible structure at whose nodes clusters of galaxies form. And these clusters are massive, hot, and dynamic bodies. So if we follow the path of a particular primordial photon in the hot ionized universe, emerging from the Big Bang, it rapidly and repeatedly bounces off the free electrons. When the hydrogen forms, and the electrons get gobbled up, it simply continues to move unchanged, except for the slow stretching of its wavelength by the ongoing expansion of the universe. Now, some of these photons may happen after a galaxy cluster, like the one circled here. In that case, the photon's direction and energy will be changed. It'll be lensed by the cluster mass and scattered by the hot, moving, electron-rich cluster plasma. And then finally, 13.75 billion years later, it's detected by an observer sitting in a solar system in the outer spiral arm of a galaxy called the Milky Way. Now, these primordial photons have seen the entire history of the universe. Everything that happens leaves an impact on their aggregate temperature and polarization. And if we can measure these impacts with sufficient precision, we can uncover the entire history of the universe. So in aggregate, we call this radiation the cosmic microwave background, or CMB. It's cosmic because it fills the entire universe, microwave because the expansion has stretched the photons to millimeter wavelengths or microwaves today, and background because the primordial photons come from behind all the astrophysical sources like stars. The CMB sky is covered with hot and cold spots of all sizes, but some sizes have more and stronger spots than others. And the precise statistical distribution of the spots of different sizes is a telltale signal of fundamental physics, cosmology, and astrophysics. Now, unfortunately, these spots are now absurdly faint, millionths of a degree in temperature and billionths of a degree in polarization. So detecting and decoding them has been a decades pursuit ever since the CMB was first discovered in the 1960s, and will continue. Has played a major role in many of the key discoveries and has big plans for the future. So to detect these tiny, tiny signals requires very, very sensitive instruments with as many detectors as possible, kept as cold as possible, with exquisite control of all the possible optical and electronic imperfections, placed as far above the atmosphere as possible, and repeatedly surveying the sky for as long as possible. And this animation shows the Planck satellite mission, which surveyed the entire sky every 6 months for 5 years. Dust in the Milky Way is very bright in microwaves, even though it's very dark in visible light. Our instruments therefore need ways to separate the Milky Way from the Big Bang. To decode the CMB sky, we use the so-called angular power spectrum. The power spectrum shows how strong the hot and cold spots are at each size or angular scale. And whatever the particular distribution of the spots any individual observer anywhere in the universe sees, the underlying power spectrum we all see is the same. And these temperature and the so-called E and B polarization power spectra contain a wealth of information. For example, this bump tells us is space curved or flat. Here we can find out how much of the universe is in ordinary matter. These wiggles tell us how many extra light particles there are. This bump tells us when the first stars formed. Remember the lensing? That converts some of the blue E polarization to the dashed green lensed B polarization. The good news is that this can tell us the mass of the neutrino. But the bad news is that this lensing signal dominates over the solid green primordial B polarization from the Big Bang, which is what tells us when inflation happens. Now we measure the epoch of inflation through a parameter we call R, and here on this plot there are 3 different values of R, and you can see that for R is 0.1, the first 2 bumps are just about visible, but as we go lower they get more and more buried under this lensing signal. So after decades of searching by dozens of experiments, in 1992 NASA's CUPID satellite finally made the first detection of variations in the CMB and proved that it was cosmological in origin. Now, although the map that CUPID made was dominated by instrument noise and of course the Milky Way across the center there, the large-scale temperature power spectrum showed the expected CMB signal, and you can see the area outlined that CUPID detected. And John Mather and Berkeley Lab's George Smoot then won the 2006 Nobel Prize for Physics for CUPID's results. And in fact, George Smoot is in fact the only Nobel laureate also to win the TV quiz show, Are You Smarter Than a Fifth Grader? In 1998, the US-Italian boomerang balloon was launched from McMurdo Station in Antarctica. You can see the launch there in front of Mount Erebus. Thanks to the annual circumpolar winds, balloons launched from the edge of Antarctica usually return to their launch site in about 2 weeks, and the payload and data can be recovered. The boomerang data were the first to be analyzed using special massively parallel software on the supercomputers at Berkeley Lab's wonderful National Energy Research Supercomputing Center, NERSC. Now, by determining the location of the first bump in the temperature power spectrum, boomerang showed that the universe is flat. When these data were combined with the cosmic dynamics results from the contemporaneous supernova experiments, including one led by Berkeley Lab's Saul Perlmutter, This showed that the universe was unexpectedly dominated by something we call dark energy. And this marked the emergence of the so-called concordance cosmology. As Natalie mentioned, about 70% dark energy, 25% dark matter, and 5% ordinary matter. And this completely unexpected result was really a triumph of the scientific method, in that we trust in the process, not the outcome. And in the process, we've quantified our ignorance to be at the 95% level. Then in the 2000s, in the 2010s, the ESA-NASA Planck satellite mission made the most detailed observation of the CMB on all scales to date. Planck observed at 9 different frequencies in order to be able to distinguish the CMB from galactic foregrounds. And you can see how the foregrounds change as we go through the different frequencies. And these data were also analyzed using the special parallel software on the supercomputers at NERSC. These data are a cosmological treasure trove, and in amongst many other things have placed the tightest constraints on inflation so far, with R less than 0.044. The Planck team won the Gruber Prize for Cosmology in 2018. However, these data also contain a warning for future experiments. The polarized sky, which I'm showing you here, is dominated by galactic emission, as the BICEP experiment found to their cost when they saw dust but thought they'd measured R equals 0.2. So what comes next? Well, led by Berkeley Lab and the University of Chicago, we're designing a new experiment from the ground up to answer 4 key science questions. To understand how the universe began, we want to know how and when did the universe inflate. To understand the contents of the universe, understand how many fundamental particles there are. To understand how the universe has evolved, we want to know how galaxies and galaxy clusters form. And we can also use these surveys as really a survey of the entire microwave sky and ask the question, what is moving or exploding every day that shows up in the microwaves? And these questions probe all epochs of the universe, sort of in order as we move through the history of time. These are the key science questions for CMBS4, but any experiment that can answer these questions will automatically enable a huge range of other science. How do we design an experiment that can reach the kind of sensitivity to measure the power spectra in this whole range shown in the plot here? So to meet our science goals, we'll need to deploy existing technologies at unprecedented scale. CMBS4 will be 10 times bigger than any previous CMB experiment and 5 times bigger than all previous experiments combined. So to do that, we'll need about 500,000 superconducting detectors packaged onto, fabricated on 500 wafers that are then packaged into 500 cryogenically cooled modules, deployed on 21 telescopes of 3 different designs at the 2 highest and driest sites on Earth, the South Pole and the Chilean Atacama Desert, to survey the sky for 7 years, to gather a data set that will continue the exponential Moore's law growth of CMB data volumes, and hence continue to need bleeding edge supercomputers to analyze. CMBS4 has brought the scientific community together in support of this ultimate CMB experiment, and with over 300 scientists at 100 institutions in 17 countries on 6 continents, CMBS4 is truly a global endeavor. Thank you very much. We will now hear from Chiara Capelli, a postdoctoral scholar in the Nuclear Sciences Division.
Thank you, Julian. Okay, so today I want to show a different approach to study the universe. And instead of looking at the sky directly, we go underneath mountains. But first, let me introduce neutrinos. You might have heard already about many particles that are around us, like protons, electrons, and so on. And all these particles interact with other particles, with materials, and based on their properties, they can be stopped by different layers of different materials, as you can see in the sketch in the bottom slides. Now, neutrino is a particle that is very light, but especially one important characteristic is that it doesn't like to interact so much. And as the cut is suggesting there, it goes through us and it goes through the whole Earth without interacting, or interacting very, very low. And why do we care about neutrinos? Well, first of all, for knowledge. So studying properties of neutrino can give us insight on why there is much more matter today than antimatter. And what we mean with antimatter, this is matter that have same mass of the normal matter, but has opposite properties and characteristics. And as Julian mentioned before, the origin of the universe, so we have no reason to believe that at the beginning there was a different amount of matter and antimatter, but something happened at one point and we ended up having a little bit of more matter compared to antimatter. And then with the evolution of the universe, this is why now we have just matter, basically. So studying these properties, we developed experiment and we developed with them a lot of technology. The shining thing that you see in the middle of the slide is a quantum computer. And for example, quantum computers utilize the same cryogenic technique that we use in our experiment. Then you have there Netflix. Netflix use data compression algorithm developed by actually a guy that worked in one of our laboratories. And so on, many technology like the internet or touch screen were developed at CERN, the collider. And there are many technology that can be useful in the everyday life that we cannot think as today. For example, geolocalization use relativity theory for it. So let me do a little step more and explain what process specifically we are looking for. So we have a beta decay that is a process that emits one electron basically and one of antineutrino, so the antimatter particle of the neutrino. The double beta decay, as the name suggests, is just the emission of 2 electrons and 2 neutrinos, while the neutrinoless double beta decay is a process that emits 2 electrons but no neutrino. And studying this process can help us understand characteristics of these neutrinos. Now, what we measure is the energy of the 2 electrons emitted. And as you see in this figure on the right, they have a different shape. We have successfully measured the double beta decay with the emission of neutrinos, but we haven't yet observed the neutrinoless double beta decay. And this is exactly what we are looking for in our experiment. So this is not so easy, and let me show why. Now you see these big numbers with many zeros. So these are the half-life for double beta and neutrinoless double beta decay. What I mean with half-life is, for example, if we consider 10 atoms, after all this year, we have half of these 10 atoms, so 5 atoms that have undergone this process. And this is something very difficult if you think that the age of the universe, it's almost 14 billion years. So how we can possibly measure this? This is, instead of waiting a half-life, we just have many atoms and increase the mass of our experiment and hope that some little percentage of them decay in a faster time, right? So how we find this process? So as I mentioned at the beginning, we go under the mountains. And in particular here, I put a sketch of the underground laboratories that where we have our experiment. This is located in Italy. And as you see, it's under kilometers of rock. And why we need to go under the mountains? So you have many particles coming from outside. And I mentioned before, this particle can be stopped by different layers of materials. So we use actually the rock to shield all these other particles, because these other particles we know already and we don't want them to end up in our detector. And especially because if they end up in our detector, they can fake, they can look similar to the process we are looking for, and they can fake or hide it. And we don't want this. But this is not enough. So in addition to the rock, we use other shieldings, for example, lead. As you see in the sketch on the right, we have our core instrument detector, that is that white cube. And all around it, there are these lead shields. And this is because we have these particles that are coming not only from outside, but they are coming from the rock of the mountains itself, or the materials that we use to build our experiment. And this is in fact coming, so these particles that are emitted, so we call radioactivity, and everyday things are emitting it. For example, bananas emits a lot of potassium, of course, in a little amount. So we would need millions of them to for us to feel bad, but we are so sensitive in looking to this process that even a little bit is is ruining the outcome of the experiment. And indeed, if you see, this picture is what our cryostat, so our instrument, looks like. And you see all these people wearing some suits. This is not to protect us, but to protect the instrument from the particles that the human body itself is emitting. And after using all these, the rock, the shielding, the suits, we still have some particles that can end up in our detector. So whatever end up that we cannot reject and it's not what we're looking for, we call background. Now you see in the right a picture of the white cube that I mentioned before in the sketch. This is actually made of almost 1,000 of these crystals. And this is the coldest cube emitter in the universe. Why that? So if you see the sketch in the top slide, this is how one crystal works. So every process deposits a certain amount of energy that it's increasing the temperature of our crystal. And this temperature is converted in electrical signal by some other sensor and component. And so this temperature increase is very little. So if you see at room temperature is this 0.000, and it's almost impossible to measure. But if we go to very low temperature, and I'm talking about minus 459 Fahrenheit degrees, this increases temperature is still little, but we can measure it. So that's why we use, and this requires a lot of technology to go to these temperatures. And we are still working on this experiment to improve the quality of the data that we get. And for example, this experiment, it's called Quarry, is taking data now, but we are working on its upgrade that is called CUPID. And this is because we want to distinguish even further the particles that are our process that we're looking for and the one that we don't want. So in addition to this crystal, we use a light detector to measure not only the heat, the temperature increase, but also the light produced by these interactions. And having both light and heat allows us to distinguish the type of particles and to reject them, and to reduce by 10 times these background, these other particles that we don't want. So here in Berkeley, both at the labs and the university, we work on many aspects of this experiment, and both on the hardware side, having some testing and developing sensor, on the data analysis, and when COVID allows, we often travel on site, so where the main experiment is located. I just want to mention that this is not the only experiment looking for this process. Indeed, there are other experiments in which the laboratories are involved, and you see here some of them. So if you're curious, you can look for them, and they use different techniques, different materials. So I just want to have a quick summary of what we have learned today. So we are looking for this particular process, neutrino-less double beta decay, to understand properties of neutrinos and to try to answer some mystery of the universe. And how we do it is basically going underground, using the rock as a shield, using additional shields and protection to remove radioactivity, and going to very, very low temperatures. And something that often people is wondering is what happens if we don't find this process? Well, of course, we can keep searching for it using different techniques, different materials, trying to develop new technology. But even if we don't find it, this is important because we can exclude some of the many hypotheses theorists are formulating. So not finding something is actually giving us some answers. And of course, in the meanwhile, we also are very interested in develop these technologies that are then applied to the everyday life. So with this, I thank you for your attention. If you are curious to know more about CUPID, we have a website, so the other experiment as well. And I will stop here my screen share. and introduce you to Satya Goncho, that is a project scientist in the physics division of the lab.
So my name is Satya Goncho, and I get the honor to close the 90th anniversary of Berkeley Lab lecture series by telling you about a terribly exciting project that has officially started less than 3 months ago. That's the Dark Energy Spectroscopic Instrument, DESI. As its name indicates, its main mission is to bring us a new understanding of what dark energy is. We had known for a while that our universe had been expanding, and in 1998, 1999, it was discovered that this expansion was accelerating. The universe was now expanding faster and faster, and we've named the culprit dark energy. That discovery was led, amongst others, by Saul Perlmutter of the Berkeley Lab's physics division, and it resulted in the 2011 Nobel Prize. So we have a universe composed of 5% of ordinary matter, you, me, galaxies, stars, 25% of matter that is very heavy, but that we cannot quite see directly, and we name that dark matter. And finally, on top of being responsible for the acceleration of the expansion of the universe, dark energy constitutes, at this time, nearly 70% of the content of our universe. So why is that so puzzling to us? We have spent the past centuries solidifying our understanding of the 4 fundamental forces, but now there is something that is responsible for making the expansion of the universe accelerate. And if you have acceleration, you have a force responsible for it. And a 5th force that we don't quite understand, that is a huge mystery. Make no mistake, the use of the word dark is less reflective of what dark energy and dark matter are than it is very revealing of our own understanding of their nature, right? In Western Europe, the Dark Ages are used to refer to an era of history where the lack of pursuit of knowledge was notable. So we know dark energy and dark matter by their effect on the visible universe, but we do not know their nature. And so because of our lack of insight in their nature, we refer to them as dark. This cartoon represents a chronology of the different epochs of the history of our universe. Moments after the Big Bang, the universe had expanded enough that light started to travel freely, and it gave us the first image of the universe, the cosmic microwave background mentioned earlier by Julian. As the universe kept expanding, going from left to right on the image here, the first stars form, then first galaxies, then larger structures made of millions, billions of galaxies are formed. However, they're not formed at random. The backbone that informs how galaxies will be distributed is dark matter. And dark matter is, in a sense, the invisible skeleton behind the visible universe. That skeleton is also often referred to as the cosmic web. What started as quantum fluctuations right after the Big Bang grew to shape this massive substructure with an incredible gravitational pull. With dark matter being the heaviest type of matter, that means that all the regular atomic matter is attracted to dark matter through gravity. And that leads us to one key point of cosmology. We use that we can see to understand that we cannot see. And that means we use the positions of galaxies that are, in a sense, light emitting units as clues of where dark matter is. So why do we care so much about mapping with precision where dark matter is? That's because we find a primordial pattern embedded in dark matter. It's called BAO, the Baryon acoustic oscillation. That pattern is visible in the CMB, and CMB S4 is going to give us a very precise measurement of that pattern 30.8 billion years ago. But that pattern can also be seen at later times in a manner galaxies are organized at different moments in the history of the universe. And you can notice from the illustration here that this pattern gets blown up along with the universe expanding. So how does that clue us in about dark energy? We want to identify the BAO pattern at different moments in time and monitor its evolution in size. If we can see exactly by how much the pattern has been blown up, we understand how fast the universe is expanding. If we understand how fast the universe is expanding at different moments in time, we can discard theories of dark energy that do not reflect what we see with our observation and keep the ones that seem to fit. We're using the scientific process to narrow down on an explanation of what dark energy is that makes sense with real world observation that we are making. And so in order to do that, we create the largest 3D map of the visible universe ever created. We look deep and really even deeper than before. And to create this precise 3D map, the Dark Energy Spectroscopy Instrument collaboration started by taking pictures of about 1/3 of the sky visible from Earth. That looks exactly like this. What you're seeing right now, these are real data, real photographs. This is a teeny tiny piece of a 5 years effort to take pictures of 1/3 of the sky. And it's actually quite a zoomed in view of this gigantic map. And this effort is called the DESI Legacy Surveys. All of our work is public. It's accessible by anyone, just at the URL at the bottom left. Then our next step is to identify galaxies and quasars for which we want detailed information. They're very precise distance from us, and we do that through spectroscopy. Spectroscopy essentially gives us the detailed specs of whatever galaxy we're looking at. We're pointing a fiber optic at a galaxy, collecting its light, then analyzing it. The downside is that we need to know very, very well ahead of time where to point the fiber, because we cannot see directly the light that we collect, not quite like a photograph. And that explains why, for the past 5 years or so, we have been doing the DESI Legacy Surveys and creating this large imaging database. With spectroscopy, the light that we collect will eventually look like this image on the right. And this, believe it or not, makes it super easy for us to tell how far away a galaxy is. Now, Berkeley Lab has taken the lead in an international collaboration spanning more than 60 institutions, counting more than 500 researchers, in making the Dark Energy Spectroscopy Instrument a reality. Over the past few years, this international collaboration has been hard at work to design, build, and install DESI on the Mayo telescope at CUPID National Observatory in Arizona. Now, I'm going to take you through the light path of the photons as they are collected by the 4-meter mirror of the Mayo telescope, and then travel through the DESI instrument. So first, the light bounces off the 4-meter mirror, and it goes through an optical system made of 6 big lenses. So on the left, you can see here one of those lenses in London, already packed in a barrel designed to contain it. All of the lenses were polished and fitted into this big barrel in the UK, and then it was all shipped to Arizona and brought into the telescope. This is one more set of pictures of the installation with taller humans as a reference. These lenses focus the light in order to correctly bring it to the 5,000 optical fibers. Those optical fibers are brought to a very precise position to collect the light of specific galaxies by being mounted on super sleek robotic heads called positioners. Now, let's take a look at these positioners. The 5,000 fibers can get to their targets within 3 minutes to match a given part of the sky. We observe that part of the sky for 15 minutes, and then we move on. On average, we have 10 hours of observation per night, and that means that we observe roughly 165,000 galaxies per night. It's just unprecedented. Then the optical fibers bring the light to state-of-the-art spectrographs. Spectrographs are the device that we use to get the detailed specs of the galaxies we're looking at. This is the white room in the Mayo telescope that houses the 10 spectrographs, and then this is a zoom on just one of those 10 spectrographs. Finally, we have the spectra of the galaxy. In other words, we're counting photons. For each galaxies, how many photons of which color? That's all we need to get the detailed specs of the galaxy. And so the light from the galaxy is traveling in a universe that is expanding, which means that the wavelength gets stretched, it gets shifted towards red. And therefore, we see galaxies to be redder by the time the information gets to us. They have kind of changed colors. And that change is a proxy for both distance and time of travel. With our spectrographs, we measure extremely precisely this redshift, this color change, which means that for every galaxy we observe, every quasar, we have a distance measurement that tells us how far, from how far back in time are the information that each galaxy, each quasar is giving us. Now, if we go back a second to this picture that we've been collecting, how do we go from this two-dimensional image from being able to construct a three-dimensional map of the visible universe? How does that help us understand what happened in the universe several billion years ago? Well, one of the greatest difficulty and accomplishment of astronomy, which is in a sense the cornerstone of our field, is our ability to correctly measure distances of galaxies and other astronomical objects. Understanding how far away they are from us, that's the key. And with spectroscopy, we are now able to put a tag with a precise distance measurement for all of the galaxies that we pre-selected. So if you look at this image with DESI, we can identify which galaxies are closest to us, and then which galaxies are a little further away from us, and then even more far away, and then even more far away. And just as a detective putting clues collected in the right order and using perspective to extract information from its clues, we're able to use 2D images of the sky to divide it into different slices of different depth and to create a 3D reconstruction of that part of the sky. But that's not all. I did mention that a distance measurement is also a proxy for going back in time. And so the deeper we look, the younger the universe we're looking at. And you do that with many, many images pointing at different parts of the sky, the larger the 3D reconstruction you get. And so the deeper we can see, the further back in time we can go and access information. So now coming back to this timeline of the evolution of the universe, CMB-S4 gives us the first picture, and DESI is now working to give us many, many, many more pictures. And if you think about it, when you put many pictures, one after the other in chronological order, what do you get? You get a movie. This is the very first look at the timeline of the universe, reconstructed with only a few months of DESI data. This 3D reconstruction contains information about the way our universe is ordered, its structure, but also its timeline, the chronology of how things came to be the way they are. And over the next 5 years, DESI will create the largest 3D map of the universe, and as such, we'll be able to make the largest fly-through video of the universe and how it has evolved in the past 12 billion years. So we will all but be able to see how dark energy influenced the evolution of the expansion of the universe. Now, I like to end with a quote from a while ago from David Schlegel, who is DESI co-project scientist here at LBL. So for the past 13 years, we've had a simple model of how dark energy works. But the truth is, we only have a little bit of data, and we're just beginning to explore the times where dark energy turned on. If there are surprises lurking out there, we DESI expect to find them. But if there's something I really want to point out, is that all of this work is a collective effort on the part of many different people and many different entities. The kind of breakthrough that DESI will bring over the next few years is the fruit of the joint efforts from this big international collaboration. We have a bright future before us to bring to light the nature of dark energy. Thank you for your attention, and now I'll pass it back to Jen Tang.
Thanks so much, Satya, for a fantastic presentation, and thanks to Natalie, Julian, and Chiara as well. At this point, I'd like to invite everybody back to the screen along with my colleague Jocelyn Delgado so we can begin our Q&A session. And as a reminder, please submit any questions you have for our presenters using the chat function or the Q&A function at the bottom of the Zoom window. So let's actually start with this question from Satya. How can we quantify the percentage of dark energy versus dark matter versus regular matter when dark energy is just a placeholder term for whatever's causing the expansion acceleration, and we don't really know what it is?
So we only know dark energy because we know it makes the universe expand, right? So now but we have people thinking about it, and they say, okay, theory number one says dark energy will make the universe and the BAO pattern to be size number one at 13 billion years ago, and then size number two at 5 billion years ago, and size number three at 2 billion years ago. But then you have another person who disagrees and says, no, my theory of dark energy says the sizes will be different at the times that you mentioned. And so as many different people thinking about it, as many different theories, more or less. And so what we do is we measure the BAO pattern at different moment in time, and then we say, okay, whose theories is getting closest to the measurements that we make. The theories that are very far away, we're like, sorry, you lose, you're not matching reality. And then we keep the ones that are close, and then we make even better measurements to be able to discriminate between them. So that's how we can see if a theory that we've come up of what dark energy is matching reality or not.
Fantastic. Thanks, Satya.
Julian, I have a kind of a fun question for you. So it's said that the CMBS4 experiment may lead to the discovery of the 9th body in our solar system, or the 10th if you're one of those people who counts Pluto as a planet. Can you talk a little bit more about that?
Yeah, so obviously what we're looking for is the Big Bang. But as I said, the fluctuations we're looking for are very, 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 very faint. So we have to make these incredibly sensitive microwave detectors and survey the sky over as wide an area as possible with this exquisite sensitivity. And one of the things that means is that anything that emits microwaves that's between us and the Big Bang, we're going to pick up as well. So we know that there are big problems there with the galaxy, with contamination from galactic dust and so on. But it also means that change on the sky, we can also pick those up. And especially with CMBS4, for the first time, we'll have enough sensitivity every single day that we can look for day-to-day variations and pick out things that are blowing up, like gamma ray bursts, which blow up a long, long way away, and their light gets stretched, redshifted as it comes towards us and shows up in the microwave. Or we can pick up things that are very close by, but that are very cold, like a planet 9, which is far enough from the sun that the peak of any emission would be in the microwaves. So if we look at our maps, our daily maps of the sky, if we see something slowly moving across the sky in the nature of a planet, that would be the detection of planet 9.
Great, thanks, Julian. So let us direct the next question to Chiara. And so somebody in our audience wanted to know, how do you control for the presence of stray radionuclides within the materials used to construct detectors like CUPID?
So when we design the experiment, of course, we need also to choose the materials we used. And what we do is, of course, we need materials that satisfy the requirement for the experiment to work, but we do what we call screening campaign. So we take several samples for different type of materials, and we actually measure the concentration of all the materials that we used in building the experiment. And we measure this concentration with spectrometers or with dissolving them in solution, measuring concentration in a way that for everything that we use, we have, let's say, a table with all the level of the amount of these radionuclides that we expect we will have also in our experiment. What we do then is we know this, and when we collect our data, we can distinguish the amount, the amount of our data that are actually coming from what we expect from these materials, and match the data with the numbers we expect. And if there's something exceeding the numbers from material, then in that case we have something that we don't know. But otherwise, we measure everything before building it.
And our next question is for Satya. Are there properties of dark energy aside from its numerical value that DESI or any other experiment might conceivably reveal?
What's exciting is we don't know what we don't know. So only by looking and getting more information, we might discover something that we didn't know is out there about dark energy. So I guess that's the best answer I can give you on that.
Thank you.
So let's actually ask the next question for Natalie. We've talked a lot about this. We don't know what dark matter and dark energy are. Is there a chance that they exist outside of our understanding of the 4 dimensions of the universe?
Well, I think, Jen, that's a pretty deep question. Dark matter and dark energy. Did you ask about both of them? Yes. Okay. So yeah, they're very different. I mean, we think that dark matter is a particle, but there are a variety of theories ranging from WIMPs, so weakly interacting massive particles, which might have masses in the billions or hundreds of billions of electron volts, or axions, which could be in the milli to micro electron volt mass range. So there's a huge parameter space for dark matter, where we have experiments searching across that full spectrum, but we don't know what it is. But we don't think that it has necessarily a direct connection to higher dimensional theories. But higher dimensional theories are very popular among theorists, especially string theorists. But as of today, I don't think there are any predictions, testable predictions from string theory for dark matter or for dark energy. Dark energy, on the other hand, we think of as not as a particle, but as a force. So perhaps some theories in higher dimensions will come up with an explanation for that. But so far, I don't think we've connected it to higher dimensions.
Got it. Thank you, Natalie.
And this next question is for Satya. What are the leading theories about what dark matter is? Is there anything that we know about dark matter now which can help narrow down what it is? Or are we still grasping at straws at this point?
I don't know that I'm the best person to answer this question, but yes, from what I understand, dark matter is classified depending on how massive it is. You have different theories that predict different masses, and so of what a particle of dark matter would be. And so when, at least from cosmology, we're trying to understand what dark matter might be, this is how we discriminate between the different theories, is by trying to infer what's the mass of one of the particle. But again, we're not so advanced. We're reducing the range of mass that a particle of dark matter may be, but we're not so advanced that now we can just narrow it down very specifically to saying this theory is the theory.
Got it. All right. So we've got another question. I think this is maybe something both Julian and Satya and Chiara can chime in on. So can your data be used to quantify how sensitive the universe's current state is on the initial conditions at the Big Bang? For example, how much would it be different on an extragalactic scale if it was slightly different on a microscopic scale initially? And there's a follow-up, which is, can you measure how chaotic or nonlinear the universe's formation was? All right, don't jump to answer, but if one of you has a thought on that question, we'd love to hear your response.
Sure. Hi, Cooper. One of the things we can certainly do is look at forward modeling. So take a particular set of the parameters of our cosmology and see how the universe would change as we tweak those slightly. And we typically don't see huge chaotic changes. Things change very smoothly. So small changes in fundamental parameters typically give relatively small changes in the ultimate outcome.
Satya or Chiara, anything you want to add to that? All right, let's maybe move to the next question. Thanks, Julian.
So our next question is, how did the DESI team determine which galaxies to map?
That's a really good question. That was a huge amount of work. We want a map that is complete, meaning we decided not to focus only, let's say, on the upper right corner. We needed to have all the galaxies that we observe that are evenly distributed over the entire footprint, which means the part of the sky that we decided we wanted to look at. And so that's, if you're looking, just scanning with your eyes, but also in depth. We don't want all of the information that we're going to get to be from galaxies very close to us. So we needed also all the galaxies selected to represent an average population of galaxy at very distances from us. So the targeting team, which is the team who worked on making these determinations, have done a tremendous job for the past few years, and hopefully soon enough now we're finalizing, this strategy, and we'll be able to display it in detail to the public.
Great. So Julian, this is another one for you from the audience. Can any information be learned from the time history of the cosmic microwave background? It's understood that instrumentation, precision, and resolution changes make this maybe a little bit more complicated, but presumably if you wait long enough, there'll be variations in time similar to angular variations.
Yeah, this is a great question. One of the big challenges we have with studying the cosmic microwave background is that we only have one realization of the universe to look at. And so particularly on the largest angular scales, we suffer from a problem we call cosmic variance, which means the uncertainty on our measurements on the very large angular scales are dominated by the fact that we've only got one view. So ideally, what we'd like to do is have observers spread all over the universe, all making their own observations of the CMB, and then pooling that would drive down that cosmic variance. We'd have lots and lots of samples of each person's visible universe. Now, obviously, that's a challenging thing to do. So an alternative, obviously, is to take views of the universe at different time. Now, the challenge with that, obviously, is you have to wait a fairly long time. We're talking about 13.75 billion years of universal of cosmic history. So today and tomorrow, the CMB looks very, 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 very similar. However, we are to a point where the time span since first detection is enough that in theory, you would see small variations, and it will give you some handle on that cosmic variance. Yeah.
So this question is for all of you. All of your experiments must generate massive amounts of data. How are you leveraging the Department of Energy's supercomputers to make sense of all of the data?
We couldn't do it without them.
Yeah, so actually, when I was first hired to Berkeley Lab, when NERSC moved to Berkeley Lab, and there was seed funding to start new collaborations between the divisions at the lab and NERSC. And so George Smoot actually brought me into the lab to start developing the code and running CMB data analysis on the NERSC supercomputers. And again, we couldn't have done it without it. As I showed in one of the plots, the data volumes have grown exact tracking Moore's law. And so we have sat on the bleeding edge of supercomputing for 20 some years now, and we'll have to continue to do so for 30 more, just to keep up with this tsunami of data.
Yeah, it will be much slower and annoying to work without them.
Great. Well, I realize we are actually at the top of the hour. That hour went by so quickly, and your presentations were just so compelling. Thank you so much. We're now at the end of our event, and before we close, I do want to thank the panelists once more for their presentations, thank the audience for their really fantastic questions, and just want to let folks know that if they're interested in staying on top of the research that's coming out of the lab, you can follow us on social media. We're at Berkeley Lab. You can always visit our website at www.lbl.gov. Thanks to everybody who's tuned in for these 90th anniversary speaker series events. We really appreciate it. Hopefully we'll see you soon with some more events to talk about the great science coming out of the lab. Thanks so much, everybody, and have a great afternoon.